let's look into flat top sampling. So flat, it's same as natural sampling. So if this is my waveform in natural sampling, we had seen that this is how the waveform went on, like it was tracing the amplitude. But in flat top, what happens is, if this is my message signal, what it will do is it will go, it will touch the reconstruction, or the message signal that we want to reconstruct. It will not raise the amplitude, it will just give you the first amplitude, and then it will be flat. It will not vary like this. So that is why the name flat top. So it will just go like this, it's flat everywhere. But in natural sampling, it was varying with the amplitude. So that's the difference here, that's all. So here, now let us take, we know that this is the same for the impulse formula that we had used. Now let us assume this is s of t. These impulses are s of t, and their width is t, and the message signal, original signal, is g of t. In the previous derivation we had used x of t, and here just we are using g of t for a change. So now I know that this is this is my reconstruction. This is ms of t. In our before derivations we are denoted it as ms of t. I am denoting it as s of t. Now when I multiply it with our impulse train, this is the equation, mathematical equation that we get. Okay, now h of t that we know that impulse train is something like this, right? One is at 0, one is at ts, one is at minus ts, and so on. Now we know that h of t is varies from, it has an width of t. So I'm representing here only one pulse, which is at 0, which goes from 0 to t and has an amplitude of 1. So I can represent it as h of t is 1 from 0 to t and 0 elsewhere. So this is my rectangular t of t minus 1 by 2. This is basically rectangular, right? So h of t, this is what you get. Now if this is our message signal and I want to reconstruct it at various points, then what we will do is, this is like for the one particular sample. So at one instant, like if I'm considering this particular instant, this is what indicates, the symbol indicates. So we are defining a discrete time signal g delta of t that results from sampling process as. So uh, I know that I get this from convolution of g delta of t with h of t. Now using the convolution formula, now I know this is equated to this, and this is the convolution formula that we have. Okay, whenever it is convolution, it is in the formula goes on like this. So now when after convolving it and I'm substituting this particular thing in this particular g delta of t, whatever I had, I'm substituting this in this here, and I'm multiplying it with h of t minus tau. I want the convolution of g delta of t with h of t, so that I get my, this is at a particular instant, right? So I'm convolving it uh, with h of t, that is my impulse train, to get my reconstructed message signal. So that's why I'm convolving, and I know that at a particular instant this is the value that I should get. So I'm substituting this in this. So this g delta of t was there, that I'm substituting here, and I'm multiplying it with the ht or t minus tau d tau. Now when I multiply this and this, what happens is it's basically indicates this h of t minus tau at tau is equal to nts, because delta of t just shifts or gives you gives you values at particular instance of time, and its magnitude is always 1. So when you multiply this both, this is what you get. Okay. So after multiplying it, this is the final equation that you get, and we know that s of t is g delta of t in convolution of h of t. And I want, this is what I got, this is the answer that I got here, but I want it in frequency domain. When I convert it into frequency domain, we know that convolution becomes multiplication. So this is why this becomes multiplication here. And now I will the formula uh, goes like this. This is basically 1 by ts, and it is written as fs here. When g delta of f is written in form of, instead of writing at one particular impulse, I'm writing it for a whole train. Like I had this particular g delta of f for only one instant. So if I want to represent it over all the instants, then this is how I write it. It will become, instead of g delta of f, this whole thing comes into picture. So it will be fs, that is 1 by tau ts, or fs the same thing, and summation over n minus infinity to infinity g of f minus n fs h of f. After that, I need to find what is h of f. So h of f, I know that when I convolve it, sorry, in the Fourier, if I take a Fourier transform, this is the formula that I have for Fourier transform. And I know that in frequency domain, our amplitude was 1, which is it was varying from 0 to t rate. We had assumed that h of t is, this is what h of t is. Now we have to find h of f. So now I'll substitute in place of h of t1, and this is how I'll solve it. I'll integrate it. When I integrate it with respect to t, or the remaining terms comes in the denominator, and it goes from 0 to t. And when I substitute t here and 0 in here, this is what I get. So uh, now I'll divide and multiply it by e power j pi ft, because I want to convert this particular thing into sinc function. So when I do that, this term will go here. When I multiply this is what I get. And when I multiply this and this is what I get. Okay. So when I solve for it from the Euler's form again, which is e power j theta minus e power minus j theta by 2j, I get a sine function. And since I want to write it in sinc function is what sine theta by theta will be sinc. So when I write it in this form, this is what I'll get in the end. So this is the waveform that I'll get for h of f. Since I'm taking the amplitude, the magnitude of h of f, these are the positive terms that I'm getting. So this is the magnitude that I get for h of f. Now let's find what is the angle. The angle is basically 1 at 1 by t. I'll get minus pi. Uh, I can get it from, wait, it is, this is what I had got, right? Now at 1 by t, if I substitute here 1 by t, I'll get minus pi. If I substitute 2 here, 2 by t, and this t and t get cancelled. That is, in place of f, if I substitute 2t, 2 by t, t and t get cancelled. I'll remain with 2f. So whatever value I get here for theta, that is pi, 2 pi, that is how it is plotted. For 1 byte it is minus pi, for 2 byte it is minus 2 pi. So connecting an equalizer in cascade with low pass construction filter. Ideally, the amplitude response of the equalizer is given by 1 by h of f. We know that h of magnitude is this, and so after solving this is what we did. So that's it for sampling flat top sampling.